Okay, it's time for part 2, and it's time to use the math that we worked out in the last lecture. So, what are we going to do with this? Let's take an example. All right, we've got a snarglefloof, obviously an imaginary animal. I don't want you to get hung up on what the animal is, okay? So we're just using an imaginary animal. Imagine the snarglefloofs have a gene for spots. 2 alleles, simple dominance and recessive, okay, easy stuff. The dominant allele makes green spots. The recessive allele makes yellow spots. We're going to use capital G, lowercase g, okay? All right, so we got 300 snarglefloofs in our population, and we counted our population, and we realized that we have 105 yellow-spotted individuals. Now, we don't have to do genetic testing to be able to figure out the genotype distribution of the rest of the population because we have our Hardy-Weinberg equations. And we know that the proportion of homozygous recessive individuals equals Q squared. So we have 105 yellow individuals out of a population of 300. We take 105 divided by 300. That gives us 0.35 or 35%. 35% of our population is yellow spotted. 35%, 0.35, is Q squared. Now, since we know Q squared, now we can figure out what Q is and then figure out what P is. All right, so if we take the square root of Q, we get 0.592. We subtract Q from 1 to get P, and we get 0.408. Check your math when you're doing these problems. Add these two together. Make sure they equal 1. Okay? Don't be me, because I forgot to do that, and I did this wrong. There were so many mistakes made while I was making this lecture. Honestly, so many. Okay, so now we know that the population has 40.8% P, 52.9% Q, so 40.8% small G alleles, big G alleles, 59.2% small G alleles. Okay. Now we can figure out the genotype of the whole population. So we've got Q squared. We started off with that. That was our 35%. We take our P, square that, we get 0.11166. That's our P squared. That's our homozygous dominant individuals. 2PQ, 0.484. That's our heterozygous individuals. So we multiply each of those numbers by 300, because remember, this is a proportion of the population. We know our total population is 300, and we get our genotype distributions. So even though by looking at the phenotypes of the population, we can't tell which individuals are homozygous dominant and which are heterozygous because of the way that gene expression works, we can do math and figure out what those proportions are probably going to be. All right, cool, right? All right, so now we can also use this to figure out if a population is evolving, because if a population is not evolving, the allele frequencies won't change. So we look at a population one generation, we look at it again in the next generation, calculate whether those allele frequencies changed, and if they did, we can say that population is evolving. All right? So here's a diagram from your book to show these calculations. We have the phenotypes. We can calculate the genotype frequencies based on those phenotypes, figure out the number of individuals, figure out the number of alleles, and what our allele frequency is. We can then use that and a Punnett square to figure out what the predicted frequency should be in the next generation. Okay, so we should have 0.49% homozygous dominant, 0.42% heterozygous, 0.09% homozygous recessive, based on the Punnett square, where we just use the allele frequencies in the Punnett square, right? How cool is that? Okay, so let's take an example. We've got a population of butterflies. The spotted wing allele is dominant to a striped wing allele. Yeah, this is a big phenotypic difference. This is not a real thing. Okay, I'm making this shit up. All right, we've got in generation 1, we have a population of 500 individuals, and the allele frequencies P is 0.6, Q is 0.4. So 60% spotted alleles, 40% striped alleles. All right, in the next generation, to keep it simple, we're going to say we have 500 individuals again. And we count up all the individuals. We have 88 individuals with striped wings, 412 with spotted wings. Is that a different allele frequency? Okay, let's find out. So we look at our individuals with the recessive allele. Those are all homozygous recessive. Okay, so that is our Q squared. So remember, this number divided by the total population gives us our Q squared. So Q squared is 0.176. Q is the square root of that. It gives us 0.420. P, to get P, we take 1 minus Q. P is then 0.58. So in generation 1, our P was 0.6, Q was 0.4. Now we have a P of 0.58 and a Q of 0.42. This population has evolved. Ta-da! We did math and we saw evolution happening. Is this big evolution? No, it's tiny. It's probably not even noticeable. It could go back the next generation. Over like 5 generations, 10 generations, this could be fairly stable. But from one generation to the next, we did see a tiny little change. That tiny little change is the main ingredient in evolution. Add up a bunch of tiny little changes all going in the same direction, and we end up with big changes. Now, if you are still at this point thinking, but how do we get from a bacterium to an animal? Lots and lots of tiny little changes, all added up together on top of each other over billions of years. Remember, so much time is involved. Millions upon millions upon millions upon millions of years. That's how we do that. Small changes adding up together. That's how we make those big changes. Okay. So why aren't populations in Hardy-Weinberg equilibrium? Because things are always happening. First of all, genetic drift is always there. There is no such thing as an infinite population. Although with mosquitoes, sometimes it seems like it, or with like ants in your kitchen, it seems like an infinite population, but it's not. Remember that genetic drift is always happening. It has less of an effect in big populations than small populations, but it still always has an effect. There's very often gene flow between populations, meaning that sometimes new alleles get added. Assortative mating, non-random mating is happening in all organisms. And yes, even in plants and like organisms like some fish that just broadcast spawn, just send their gametes out into the water. Yes, even there is some non-randomness to the mating. The gametes themselves can preferentially bind with other gametes. Again, beyond the scope of this class, but yeah, that's shit's happening. Cool, right? Okay. And environments change, and because of that, selective pressures change, and selective pressures are always happening in every environment. So that's why populations almost never in a Hardy-Weinberg equilibrium. Like if they are for a little while until the environment changes. Okay, so that is that. Now, for the next section, we're going to talk about some ways that these ingredients work together to shape populations and how we measure those things.